All right, okay. I'm not sure about the quality of light, but it should be fine.
Yeah, it's absolutely fine. I just want your words. That's it.
The lighting, how is it?
Yeah, it's good. It's perfect. It's perfect. It's absolutely
All right.
fine, sir.
Okay,
Yep.
thanks.
You know, I
Thanks.
think I think it's just because of I don't care whether the video gets the views or not, but you know that satisfaction of interviewing the person whom I actually admire, not as a person but through his work. You know, that's actually something huge for me. You know, I don't care about the views. I
Thank you
don't
very
care
much.
about the
Thanks.
subscribers. I just want the
Thank
speakers who talk with me to just go out happy. That's the only point of all my. I
All
read
right.
your book probably 25%, not even 25%. I just completed 128th page of the book and it's like amazing. No,
Thank
I
you.
just ran the
Thanks.
code. I just ran the code for a while and I just okay, fine. It's time for
Thank,
conducting the interview, then just going on. So thanks to
thank you
Dr.
very much.
Makamis. Yeah, you know,
Thank you.
thanks.
Thank you very much. Thank you.
You know,
Can you hear me?
thanks. Yep, I can hear you. I can hear you. Thank,
Okay.
thanks to Dr. Makhamisa for giving me for that amazing piece of hard work which he has written. You know, it's an amazing book. Watchers, if you are watching this podcast, please do buy that book. Just go code code your heart off. Quantum World is something like as LinkedIn profile pic also says that Alice, you're the one for me, and the Alice reply saying, Bob, I'm in the quantum world. How can you be so sure about it? You can just code your heart off and you can just feel that essence of actually doing the work and that information theory of the quantum world. It's simple Python interpreter which is working on that. So just make sure that you just work on it. So, Dr. Makamisa, I think let's just start with the podcast then.
Thank you very much. Thanks. We can
Yep.
go ahead.
Yep. You know what, Doctor, I just wanted to ask you this one question because you are in a quantum world. You have done your PhD also, and you have actually given the book for the information theory of it. So I just want to ask you this silly question from my side. What's the role of conspiracy and philosophy in science today?
I think in some cases, people make some of the conspiracies that turn out not to be true. But in some cases, you can see the people who are, whom we can say are marginalized. They come up with some of the great ideas that end up being pursued and then coming up with some interesting results. So I think at times, as much as conspiracy is bad, but what's important is the evidence. If there's any evidence to support a certain, no matter how out of ordinary or out of mainstream the idea might be, as long as there's an evidence to support that, I think that's what matters. There are issues of the philosophy. I think quantum mechanics, because of some of the interpretations of quantum mechanics, it's important for people to be familiar with philosophy so that they make arguments which are cogent, which are philosophically sound. I think so philosophy plays a crucial part in quantum mechanics, I can say that. And also some of the ideas. I think there's this book, I think it's by David Kaiser, how hippies saved quantum physics. It's a good book because it shows, especially about entanglement, how some of the physicists whom ideas were found to be very out of the mainstream, like on the edges, but they pursued those ideas, they lived the lifestyle they lived, and then eventually their ideas ended up being tested, and then they found to be okay. I think that's the group of people that actually pushed entanglement to where it is now, to the mainstream, if I could say that. Yeah. So having such ideas is important, but also after having the ideas, it's important to look for the evidence if they're supported by evidence or not. Thank you very much.
You have written a book on information theory. I just want to ask you, where was the motivation all about? Of course, you have. Doctor?
Yes, I'm still around. Sorry, I'm still around.
Yeah. You wrote a book on information theory, and your PhD is on information theory using the quantum mechanics. So I just want to ask you this one question: what motivated you to write a book?
I think the motivation, especially for me, was to make quantum mechanics, quantum computing, and quantum information in general to be more accessible to the people, to show the people that actually these things are not just done in the labs and everything. We can also try something that is hands-on for people to learn, to sort of to demystify the field so that it could be accessible to most people, especially software developers, to know that actually they can make quantum computing. And I still think because it's a new field, relatively new, when we have more disciplines working on the quantum information, it could be much easier. It could lead to some interesting results. Yeah. So that was my motivation, to make quantum computing accessible to people who are not familiar with the field.
Now, what is computer architecture to you as a quantum physicist or a person who has a PhD in quantum domain? So, what is a computer to you?
If I could summarize a computer for me, the way I understand it, you have some inputs and then you perform a set of operations and then you get an output. In a way, I think in the high level, it's how the computer should work. You have a set of inputs and then you perform some of the computations and then you get an output as the result of that computation. So it's basically that. So we can have computers which are, what do you call it, classical or conventional computers that we are familiar with. You can also have quantum computers that actually work on the principles of quantum mechanics. I think that's the difference. But the history of computing, I think, dates way back, like from the times of Charles Babbage all the way. There's also a good book by Professor Scott Aronson of, I think he's in Texas, University of Texas now, Quantum Computing Since Democratized. It's a good book also on the introduction to computing all the way up to quantum computing. So I think it's a good book.
Yeah, even Scott Aronson has an amazing TED Talk. Amazing TED Talk. I think people, if they watch it, they're just going to just grab onto that topic. But I just want to ask you this one question. What is a quantum computer? Is it just like trying luck or mimicking probability, or else is it like maybe inducing consciousness to a machine? What is quantum computing to you? Because I just want your insight on it. Broad insight. Actually, you can explain it for a long time. I don't mind.
All right, no problem. I think with the quantum computing, the difference from the conventional computing is the way the principles or the concepts that are being employed. In this case, we use some of the concepts from quantum mechanics. We are familiar with our 0 and 1, where we just use the charge to say it's a certain voltage or charge value for voltage. You can say this is our 0, this is our 1. But in this case, we can have a superposition of states, which is one of the concepts of quantum mechanics, the superposition. So it uses some of those concepts like superposition, like in some cases, some models of quantum computing use what you call tunneling, where the quantum state can tunnel through a barrier. So basically what it does is that it uses quantum mechanics to actually perform computation. That's the whole idea. It's a more of a new idea of looking at computation. The idea is actually to provide quantum advantage over our conventional computers. If you could show that in some problems, quantum computing performs better, that's the idea.
No, but like we have quantum tunneling. That's true because that's somehow working, and we are basically just getting the concepts right. But there is something called as chronic penny model, which is actually mimics how an atom is. I know it's off the topic, but like I just want to ask you this one question: how has the atomic structure of a molecule really influenced quantum computing in terms of anything as an algorithm today in the quantum world? Of course, we have seen algorithms evolve based on the molecular theory. Of course, there is Pauli's exclusion principles, Dirac functions. All these are coming up. Like, how have you understood the evolution of the quantum algorithms from your perspective? How have they evolved over the years?
Oh, I think the key, in my opinion, there's already what you call quantum cryptography, but for computation, the key, I think, breakthrough came around 1994 with what you call Shor algorithm by Peter Shor. But even before that, we also had, I think, around 1982, is it 1982 with the Deutsch algorithm? The idea was just to show that quantum computing can perform faster. And then the key to actually give the skin to quantum computing was the idea of Peter Shor to show that actually quantum computing can be used to break security of our crypto systems now. And then another idea was around 1996, I think, by Love Kruger to show that we can use quantum algorithms that could perform faster than our normal search algorithms. And then since then, there's been a lot of progress, including, I think, is it 2 years back, when Google showed that they constructed the circuit that could show what they call quantum supremacy over classical algorithms. Yeah, so yes, yes. So there's been quite an interesting progress in that. So that's why it's important for difficult players to come into play, not just for physicists. If you also have computer scientists, developers, all the people, then it could make the job quite easier. Yeah, but it's an interesting field with some interesting developments. Yeah.
Like, what is quantum computing engineering challenges? What are the not canonical problem statements that are still yet to be solved in quantum computing?
Sorry, I didn't get that part.
What are
Some
the
of the problem.
canonical problem statements that are yet to be solved in the quantum computing that is not still
Oh,
being solved?
oh yeah. Thank you. I think the key ones, in my opinion, some of them are the error corrections. How do you build scalable systems? Now we are in the era of what we call NISC, or noise intermediate scale quantum computing. So it's mainly about few qubits that can be developed to run the codes. I think up to 53 for some systems like Google systems. Others it's 15 qubits. So the key issues are how to make the quantum computers more scalable, to have more qubits, because in order to implement some of the algorithms, we might need millions of qubits, logical qubits, but it's not, for now, it's not feasible because of error correction issues and scalability issues. So I think error correction is the key problem now. How do we correct the errors in the system in order to make scalable quantum computers? So I think for me, that's one of the key challenges. And also another challenge is actually to perform, like we do in quantum machine learning. We can develop an algorithm for quantum machine learning, but it's important to show that actually it outperforms the classical counterpart, the best classical counterpart. I think that's another problem. It's interesting to have a new algorithm, but the issue is, does it actually outperform its classical counterpart? That's another key issue.
Yeah,
Because you remember even the Google supremacy one, I think the researchers from IBM said actually they can simulate that using the classical computer, the supercomputer. So it might turn out that actually doesn't provide that quantum supremacy that they were talking about. So it's important to actually come up with algorithms that actually outperform the classical counterparts using the NISQ era, NISQ
yeah,
systems.
of course, quantum supremacy was never being completely achieved. I think so because it was quantum advantage to one extent. I think so. Probably we have not gone to a stage where we have achieved quantum supremacy. I think I just want to ask you this one question. What's the key thing that we are looking for in a quantum computer tomorrow? Basically, I'm asking you, what will be the form factor of a quantum computer tomorrow?
Beyond NISQ, or within the NISQ era, if it's
Yes.
beyond NISQ, then beyond NISQ, we'll expect the system that is actually robust against errors, that is much scalable, that can implement all the algorithms, that like show algorithm with reasonable number of qubits. Yes, so that's what we're looking at. But now, unfortunately, we are still a long way from that. I think it might take some time. Oh, and the issue of quantum supremacy, there was another paper, I think it was from, can't remember the group from China. They said they managed to achieve quantum supremacy using photonics. So I don't know if that will stand the scrutiny, but it's something new, relatively new. So maybe with time we'll see if it actually breaks. Yeah.
What are the errors of coding such machine? What are the horrors of coding such machines? Anything which can go wrong while we are coding a quantum computer. What are those?
Maybe because the systems, when you do that, the systems, they have very short coherence time. So by the time you're trying to manipulate the systems, these qubits, you might find that the coherence, they lose coherence, they decohere. So they lose that coherence. Then they turn to classic. They are so many classical states, so they cannot be manipulated anymore. So I think decoherence is the huge enemy or noise the system. So it's very difficult to deal with the systems due to decoherence.
What's your view on the new AGI which is going to be involving quantum computer, the artificial general intelligence which will be involving quantum computer? Is it really an form factor that we can really expect tomorrow?
I think my views on the AGI in general, I think you know Professor Andrew Ing, he was said, yeah, it's
Yeah.
my views. I tend to have the same views as he is, because maybe the issue of focusing on AGI might be too soon. It might be something that we might not have to worry about now, in the sense that we're not too sure if we can gain that much of conscience from the systems that we're using now, which are basically mechanical systems. So maybe, like he said, with an analogy that he's using, maybe it might be like discussing how people can colonize Mars or something like that. Maybe a bit, in my opinion, maybe it might be a bit early. You might need to see that it's possible first physically, and then once it's possible, then we can start discussing that.
Yeah, you talked a lot on your quantum world, how they are just going to be. Like, how is the quantum communication all about to you? Because it's all about the information theory that you have written. But like, how is it going to help in the future communication? Blockchain has been used in understanding or basically mining Bitcoin. Quantum computing has been influential in that field also. But like, I'm asking you, like, where can this quantum computer fit in this present world?
Oh, in the present world, there are actually some interesting applications, like with quantum communication. We know that we can have what we call quantum cryptography, which offers a better security than normal cryptographic systems. So that's one of the advantages. Another advantage of quantum information, when we focus on quantum computing, is what we can solve within chemistry. Some of the quantum chemistry problems require quantum mechanics. They seem to be working well with quantum mechanics. Other people are also exploring different fields, like in finance. Actually, are working in finance to see if they can implement those. So I think the use cases of quantum computing will increase with time. And then there's also with quantum machine learning, we don't know how far we can go with that. Yeah,
Yeah,
I
but
expect
like,
to,
you are expecting about the financial world. That's for sure. Somehow they are going to get it, because financial people don't care whether you solve it through a conventional computer or through a quantum computer. They just care you just need to solve the problem. That's it. They don't care about throwing the machine cycles.
uh,
But there's an huge gap, but that has been filled today. Game theory and the quantum computing. I think you should be knowing this, because game theory has been such an influential one. And I think probably I just want to ask you this one question: how is game theory and your quantum computing, the combination, going to give a huge demand in the compute tomorrow? Also, how is it going to change the world?
yeah, they're also interesting. Thank you. There are interesting applications of quantum computing, like using what you call quantum games. So I think there's another interesting field that is worth exploring. I think I also discussed a bit of that in the book. Maybe you haven't gone through that chapter. Yeah,
Yeah,
so it's
yeah,
an
I've not
interesting
gone through
field
that
that is.
chapter.
Oh, sorry, sorry for that. But it's an interesting field that is actually worth pursuing. But there's also this marriage of quantum computing with game theory. So it's quite interesting. It's quite interesting.
Yeah, but like, will the quantum be the new AGI? That's what I'm asking you, because there are new ways in which quantum computing have come up. Like, probably quantum computing, even with the 16-bit, we can achieve something which is not possible even by a 64-bit computer. That's what I feel about. Will quantum computer be the new leverage for the computing, or else how is it all about?
Yeah, in terms of computation, it will allow us to solve some of the problems that might not be tractable with our normal conventional computers. So the speed up normally is for most problems, either it can be exponential speed up from our normal computers, or we can get normally, like for search algorithms, you can get quadratic speed up, meaning if we have, unlike maybe with our normal cores, if we increase the number of cores, we might find that we just get constant speed up, polynomial speed up. So in this case, it means we can solve some of the problems that are intractable quite faster with quantum computers. So that's why it's very much attractive to explore that route. And it's
You know,
also good to think about quantum computing in the context of the fourth industrial revolution, because if you explore like technologies like blockchain, artificial intelligence, you can also focus on also on quantum computing and what it can bring to the fourth industrial revolution.
In your book, you have talked about exploring quantum circuits, how to actually explore a quantum circuits and how to actually build our own quantum circuits tomorrow. That's my question because that's the hot topic that I wanted to cover today.
Okay, with I think with our normal circuits, we know about the logic gates like the AND gates, the NOT gate, and other gates. So with quantum computing, we can have some of the gates can be what you call that turn a quantum state into a classical state. They're just measurement gates. Or we can also have a lot of unitary gates that actually keep the structure. So normally, for people who did linear algebra, most of the gates are just unitary matrices that we use for quantum computing. So you can have some of the gates can act on a single qubit, or it can have multiple qubit gates. So that's basically what we do. So from linear algebra, it's just actually using the unitary matrices for if it's
Yeah, moreover, like we have discussed a lot.
I can hear you. I can hear you.
Sorry. I was muted. We have discussed a lot about your book and we have talked a lot about technologies that are being used. What are the actual frameworks that we really need to be sturdy? Actually, we need to be clear in concepts in order to use these frameworks. What are those concepts that we are supposed to have prior when we are working on quantum frameworks?
Oh, I think some of them, like I mentioned, the issues because when we implement on the frameworks, the issues like entanglement. In some cases, we have to understand what entanglement is. We have to understand superposition, and in some cases also tunneling. But what's good about the current frameworks that we're using is that they're very much high level. So in some cases, you might not need to know much about the hardware entanglement, everything. But those are the concepts that we need to understand so that we can use most of the frameworks that are available. So from the software development perspective, it's much easier to interact with the frameworks that are already available now. So a bit of quantum mechanics is needed and a bit of linear algebra, which shouldn't be a problem for most people. But when you go to quantum machine learning, you might need other advanced mathematics concepts. But linear algebra, I think, is the basis for everything in quantum computing. Yeah.
No, but I wanted to ask you this question, I wanted to ask you this very question. I think this is the last question that I want to ask, and we are going to go for part two in the next week, I think so. Next week, anytime that you're free, we'll be going for the part two. I just want to ask you this one question, like what's the most beautiful concept that you have come across in quantum computing or else in the mathematics?
Uh, I think I'll say linear algebra. Even from machine learning, because I also work with machine learning, I found linear algebra to be quite useful. It's also useful in quantum computing, which is, I think, I'll say the beautiful ideas and is will be linear algebra in general. Because once you know that, I think you're well equipped to work in most of the stuff that we have. So for me, I'll say linear algebra.
So thank you so much, Dr. Makhamisa, for giving this amazing podcast. It's actually a passion for me to work in quantum computing. I wanted to write a paper, I want to write a book. I think this is going to be my first step towards demystifying your complete quantum computing that I've come across in my world. I think it's going to be much more effective if we just do the part two, part three, if possible, part 10. I don't care. Thank you so much, Dr. Makhamisa, for just giving this amazing podcast. I think I enjoyed it a lot. It's not about the work that you have done. It's not about the book that you have written. It's all about that, you know, it's all about the concept that I got cleared after reading the 128 pages of that book. I'm supposed to read a lot, but after reading some, I cleared some of the wrong aspects, some of the things which I failed to explore. I think that actually helped me a lot. And thank you so much for that.
Thank you also for giving me the opportunity to discuss these issues. Thank you very much.
Yeah, I know.
Thank you.